Hi everybody. So we talked about the ideal gas law, PV equals nRT, and we did a dry ice lab to calculate what the value of R is. And we said that the literature value is 62.4 millimeters of mercury times liters per mole Kelvin. That's a number that you have to memorize. Hopefully we'll use it enough that you will know it. You will also need to know it in terms of different units of pressure. So the 62.4 if you're using the pressure in terms of millimeters of mercury, but you have to know it in kPa and in ATMs as well. So there's three different numbers that you really need to know. Let's say that you forgot that number on the test and you don't know what it is. There is a way to calculate it on the test. So you know that R is equal to P times V over NT. Think of a situation where you would know all these four variables. Well, we know that from the moles chapter that at STP, at standard temperature and pressure, 1 mole of a gas is 22.4 liters. So the 1 would be the moles, the 22.4 liters would be the volume, and standard temperature and pressure, standard temperature is 273 Kelvin, and then standard pressure could either be 1 atm, 760 millimeters of mercury, or 101.3 kPa. So you can plug in whatever units of pressure you'd like with 22.4 liters, 1 mole, and then 273 Kelvin, and that will give you the value of R. So on the next slide here, this is exactly what I have. So P times V over NT. You'll notice that all of them you have 1 mole for the amount. You have 273 Kelvin for the temperature, that's standard temperature. You have 22.4 liters for the volume because 1 mole is 22.4 liters of STP. The only difference here is that the standard pressure, here's in units of ATM, here it's in units of kPa, and here it's in units of millimeters of mercury. So this is the one that we got in our lab, 62.4 millimeters of mercury times liters per mole Kelvin. In kPa, it's 8.31 kPa times liters per mole Kelvin. In terms of ATM, it's 0.0821 ATM times liters per mole Kelvin. So these three numbers are three numbers that you need to memorize in order to be able to use them on your test. But if you forgot them, you can calculate them this way. So we know that the ideal gas law is PV equals nRT. We can rearrange this to solve for R like we did it for our lab. So R is equal to PV over NT. Now if you have a gas that we could measure these four variables for and we divide them together, that is equal to R. If we have a totally different gas or the same gas at different conditions, if we measure PV and NT and divide them by each other, that would also equal to R. So we can set that P1V1 over N1T1 is equal to P2V2 over N2T2. This is useful if we have a gas where we're changing the conditions for it, or if we have two different gases and we want to compare between their values. And this is called the combined gas law. So this is the ideal gas law, this is the combined gas law. So looking at the ideal gas law, PV equals nRT, and the combined gas law, when would you use which one? Well, the ideal gas law, you would use it if you don't have changing conditions. You have only one gas and you have three of the four variables. So R is a constant, you know that. So we have four variables. If we have three of them and we're solving for the other one, that's when you would use it. So when you don't have changing conditions, no changing conditions. The combined gas law would be if you have changing conditions or changing gases. So if you have two different gases where you're comparing between them, or if you have one gas where you have changing conditions, you change the volume or the pressure or the amount or the temperature. Let's try some problems. So the first example says, how many moles of a gas at 100 degrees Celsius does it take to fill a 1 liter flask to a pressure of 1.50 atm? So first you check Do you use the ideal gas law or do you use the combined gas law? The best way to do that is I like to go through and label all my numbers as what variables they are. So how many moles? So that's an N. 100 degrees Celsius, that's a T. 1 liter flask, that's a V. And 1.50 atm, that's a pressure. You can see that I only have one of each of the variables. I don't have two pressures or two volumes or two temperatures or two amounts. So that means I don't have changing conditions. I have just one gas at a certain temperature, amount, volume, and pressure. And so in that case, because I don't have changing conditions, I use the ideal gas law, the PV equals nRT. So I plug in my values in. So my pressure is 1.50 atm. My volume is 1.0 liters. N is what I'm solving for. R is not given to me, but it's a constant that I know. And because my pressure is in ATM, I have to use the R value that has ATMs in it. So that's the 0.0821 ATM times liters per mole Kelvin. And then my temperature, I'm given 100 degrees Celsius, but I can't use any gas law unless it's in Kelvin. So I need to convert that to Kelvin, so that would be 373 Kelvin. It's important to include the units for all of your numbers. That way you see whether they cancel or not and what units you end up with. So in this case, I will take my PV over the RT to solve for N. And so if you look at it, the ATM will cancel with the ATM, the liters will cancel with the liters, the Kelvin will cancel with the Kelvin, and when I move that over, it will be equal to some number, and then the units would be moles. So if you take 1.5 times 1 over 0.0821 times 373 and plug that into your calculator, you end up with 0.0490 moles. And that's my answer, 360. Let's look at the next example. Example 2 says at 60 Celsius, a 1/10 liter sample of a gas has a pressure of 75.6 kPa. What would its volume be at STP? So I'm going to go again and look at my different numbers. So 60 Celsius, that's a temperature. And I'm going to go ahead and convert it to Kelvin because we can't really use Celsius, so this is 333 Kelvin. That's my T. 1/10 liter, that's a volume. Pressure is 75.6 kPa. And then it says, what would its volume be at STP? So it looks like this is another volume. So that means I have changing conditions. So I can go back and label this as T1. This is V1, and this is P1, and then V2 is what I'm solving for, and then it says that STP. STP stands for standard temperature and pressure. Whenever you see standard temperature and pressure, write down what those numbers are. So standard temperature is my T2. It is 273 Kelvin. And standard pressure is my P2. Now standard pressure could be 1 atm, 101.3 kPa, or 760 millimeters of mercury. In this case, I'm going to use kPa because my P1 is given to me in kPa. So I'll use the 101.3 kPa. And as you can see, we have two temperatures, two volumes, two pressures, so definitely looks like I have changing conditions. So I use the combined gas law, which is P1V1 over N1T1 equals P2V2 over N2T2. And I plug in my values. So my P1 is given to me as 75.6 kPa. My V1 is 1/10 liter. N1 is not given to me. It doesn't give me anything about amount. Now, it says that that sample of gas is changing its temperature and pressure and volume, but it's the same sample of gas, so that means my amount is the same. When your amount is the same, or when anything is the same on both sides of the equation, you can cross those out. So because my amount is the same, N1 and N2 can cross out. Same thing if my temperatures were the same, I can cross them out, or if my pressures were the same, I can cross them out. Now, there is a longer way to do this. You could plug in your first temperature, volume, and pressure into PV equals nRT to figure out what the N is, and then use that into another PV equals nRT for the second one, but that's really long. It's equally correct, but it's just longer. So I'm going to choose to use the method we're using now with the combined gas law. So N1, I'm going to cross that out. T1 is 333 Kelvin. So that is equal to P2 is standard pressure, 101.3 kPa. V2 is what I'm solving for. And then T2 is 273 Kelvin because it's standard temperature. So to solve for V2, you cross multiply basically. So you do 75.6 kPa times 0.1 liters times 273 Kelvin divided by 333 times 101.3. Let's look at our units, what cancels from them. So kPa cancels with the kPa, the Kelvin cancels with the Kelvin, and you end up with your volume in liters. My volume, my V2, ends up to be 0.0612 liters, and that's my answer. For these, it doesn't matter what volume units you used, as long as V1 and V1 or V2 are the same. It doesn't matter what pressure units you use, as long as both of them are the same. So in this case, they're both kPa's. Temperature has to be in Kelvin all the time. Amount has to be in moles all the time. But the pressure and the volume could be whatever units, as long as P1 and P2 are the same, V1 and V2 are the same. When you're using PV equals nRT, though, you have to be a little bit more careful with your units. The volume always has to be in liters, and the pressure should match whatever the units for R are. Let's look at example 3. It says, what pressure would 3.55 grams of argon gas be under in a 2.40 liter cylinder at negative 35 Celsius? So I'm going to go and label all my numbers here. So what pressure, that's a P, and I'm looking for that. 3.55 grams. Now, that's not a P or a V or an N or a T. It's a mass. So if you think about it, though, mass can be used to find amount. So I'm going to put an N there, but just be careful that that's not moles. This is grams, and so I have to convert that to get to my amount, my moles. Of argon gas under 2.40 liters, so that's a volume. And negative 35 Celsius, that is a temperature. However, whenever I see Celsius temperature, I always convert it to Kelvin when it's talking about gases. So to negative 35 Celsius would be 238 Kelvin. Okay, that's all the numbers I have. So it looks like I have one pressure, one amount, one volume, and one temperature. No changing conditions here, and so I would use the ideal gas law, PV equals nRT. So I'll plug in my numbers. P is what I'm looking for, so I'll just keep it as P. If you want to use X, you can. V is given to me. It is 2.40 liters. N, I'm given grams, and so I need to find moles in order to plug it in. So I'll do that on the side here. Let me do it in a different color. So I have 3.55 grams of argon. I'll change that to moles. So 1 mole of argon. The molar mass of argon is 39.9 grams. And so this is 0.0890 moles of argon. Now, I chose to put it on the side, calculate on the side and plug it in. If you want to do it all together, you can. It's totally up to you. So 0.0890 moles. R is a constant. You could use, in this case, whatever R you want. If it specifically tells you to calculate the pressure in certain units, then you have to use those. But if it doesn't tell you, you pick whatever you want. Most people like ATMs, so let's calculate our pressure in ATMs. So then we're going to use the R that has ATMs in it. So that would be 0.0821 ATM times liters per mole Kelvin. And I know it's a lot of work to write all the units, but you really need to. And then 238 Kelvin. So then your pressure ends up being 0.846 ATM. Let's look at our units to make sure that those are the units that we end up with. So my liters cancel with my liters, my moles cancel with the moles, Kelvin cancels with the kelvins, and I end up with ATM. If I use different units for R, then I would get different units for the pressure, which is totally fine in this one. Let's look at the next one. Example 4 says, what is the density of bromine gas that fills a 52.5 liter cylinder at 145 Kelvin and 583 millimeters of mercury? So I'm going to go again and label my units. What density? So I'm looking for density. I'll put question mark density, and density is mass over volume. I know that. It gives us a volume, it gives us a temperature, it gives us a pressure. So I'm going to rewrite the density equation here. Density is mass over volume. Now, I'm not given the mass, but I'm given the volume. The volume is 52.5 liters. So all I need is to figure out what the mass is so I can plug it in, right here. So let's see if I can find what the mass is. I'm given only one set of conditions here, or like one volume, one pressure, one temperature, and so I could use the ideal gas law. I'm given the pressure, I'm given the volume. I know what R is, it's a constant, I'm given the temperature. So what I could do is I could solve for the amount for the moles, change it to grams, and then plug it into here for the mass. So it's kind of the opposite of what we just did. So let's do that. I'll do that on the bottom here. So PV equals nRT. So pressure is 583 millimeters of mercury. Volume is 52.5 liters. N is what we're solving for. R, since I'm using millimeters of mercury for my pressure, I want to use the 62.4 millimeters of mercury times liters per mole Kelvin. And then my T is 145 Kelvin. That's pretty cold. My N, if I do that, ends up being 3.38 moles of bromine. But I wanted the mass, so I can plug it into my density equation. So I'm going to change that to the mass using the molar mass. So 1 mole of bromine. Bromine is diatomic, remember, it's Br2. So 1 mole of bromine is 159.8 grams. And you multiply the molar mass of bromine by 2 because it's Br2. So this gives you 540.6 0.1 grams all around at the end of Br2. So now that I have the mass, I can plug it into my density equation. So 540.1 grams divided by 52.5 liters, and I end up with 10.3, and my units would be grams per liter, and that is my answer. So let your units guide you, and you will get your answer. Let's try one more. So example 5 says a gas occupies 4,430 milliliters at 30 Celsius. It was transferred in a 3.5 liter cylinder. What is the new temperature? So I'm going to label my numbers. So this is a volume. This is a temperature, and I'm going to go ahead and change it to Kelvin. So that would be 303 Kelvin. Then it says another volume. So I'm going to go back and label these as V1 and T1. And then this is going to be my V2. And I'm asked, what is T2? So it looks like I have changing conditions. So I'm going to use the combined gas law. Now, the combined gas law really serves as an alternative for all the 4 gas laws we learned. Remember Boyle's, Charles, Gay-Lussac's, and Avogadro's. If you know the combined gas law, you do not need to use any of those 4 because you can get them from the combined gas law. For example, in this case it mentions volume and temperature changing. It does not mention anything about amount changing. So like a previous example, since the amount is not changing, since I have a gas and I'm transferring it from one vessel to the other, I could cross out my ends. Also, it doesn't say anything about the pressure changing. If it doesn't mention it, then that means that it's not changing. So if the pressure is the same on both sides, I can cross it out as well. And so look at that. I'm left with V1 over T1 equals V2 over T2, which is Charles' law. If you cross out your amount and temperature because they're constant, you'll get P1 V1 equals P2 V2, which is Boyle's law, and so on. So whatever 2 variables that are constant you cross out, you're going to get the equation for the gas law that you're looking for. So no need to remember now any of the 4 really if you know the combined gas law. So I'm going to use V1 over T1 equals V2 over T2. I'll plug in my numbers. So my V1 is 4,430 milliliters. My T1 is 303 Kelvin. My V2 is in liters, so I need to convert that to milliliters. So either you convert both of them to liters or both of them to milliliters. It really does not matter which one if you're using the combined gas law, because you have a V1 and a V2, they're going to cancel out. If you're using the ideal gas law, PV equals nRT, then it has to be in liters because your R units have liters in them. So anyway, I'll convert this one, so 3,500 milliliters, and then T2 is what I'm solving for. And if you plug that into your calculator, you end up with T2 as being 239.4 Kelvin. And you can leave it that way. It doesn't really specify what units they want for temperature. If they asked for Celsius, it is negative 33.6 Celsius. But either answer is fine.